Good day, ladies and gentlemen, and we are back again together. All right, the last time we were together, we were looking at organic chemistry. I'm sure you're probably thinking, hey, but I've seen this one before. Okay, remember this was the last one that we did, but today we're going to be focusing on question 5. So maybe let me just hide the other part there. All right, so if you haven't subscribed, hey, do the right thing, hey, just become part of the family. And thank you so much, guys, for the wonderful comments that we're getting. Sometimes you guys just fill me to tears, when you give those comments about how well you've improved. And this is exactly the reason why we created this channel, for your benefit. And I just think it would kind of be selfish in a way if you keep that to yourself. So please just make sure that you tell your friends about it. Tell them your secret. Tell them why you've been getting those level 7s and why you are improving all of a sudden from level 2 to level 6, whatever it is that's happening. Okay. So we owe it to each other to empower one another, and that's the reason we created this channel, so that more and more of you could benefit. Okay, right. So I'm going to be looking at question 5, which has to do with rates of reactions. I know that some of you guys really struggle on this part. If you find that some of the questions are a little bit daunting, just make sure that you go and watch our the full video, the full lesson on rates of reactions, and I'm sure that by the time you'll thank me. I promise you, you will definitely thank me. Okay, so let's have a look at the question. Okay, so question 5. All right, so we are looking at the study. They say study the Maxwell-Boltzmann distribution curve. If you want to know what this is about, please, as I said to you again, go and watch that video. Okay, they say of a certain reaction. Now, they say P and Q are labels on the axis. What quantity is represented by P, right? For those of you who already know, we know that this would represent the kinetic energy, isn't it? Okay, so this would be the kinetic energy. So at that point there, this would be the average kinetic energy. If you remember, we always talk about average kinetic energy in terms of rates of reactions, right? So, sorry, 5.1.1 rather. Where's my mind? Right, so P represents kinetic energy of molecules. So this would be kinetic energy of the molecules. And then Q, 5.1.2. Okay. Q, which is on the y-axis, this would represent the number of molecules. Okay. Right. So in this case, this would be the number of molecules. Okay. Really, there isn't too much here. You just need to remember that. Okay, so yeah, so that you know it for the future. Right, let's have a look at 5.2. They say line R represents the minimum energy required for the reaction to take place. By the way, that is called activation energy, right? So they say write down the term for the underlined phrase. Okay, we've just said it. Okay, so that would be the activation energy. Okay, what that means, ladies and gents, that line there, it means that molecules, okay, that have not passed this point here, the minimum energy that is required, would not undergo or would not experience or would not have effective collisions. So yes, they would still collide, but the result of that collision would not be a product. They would go back to being reactants. But these ones here, remember that the condition for a reaction to take place, an effective reaction or effective collision to take place, is that there must be sufficient kinetic energy. So above this point here would be sufficient kinetic energy, so they would undergo what we call effective collisions, right? Right, so 5.2.2. Okay, they say how will the shaded area on the graph be affected when a catalyst is added? Now remember, the moment we add a catalyst, what it does is that it lowers the activation energy. I'm not going to explain much about it. Okay, so they say, how will the shaded area? So the shaded area would actually increase. So if you think about it, it would, when you add a catalyst, you would actually bring that point closer in this case, so there'd be a greater area, greater shaded area. So the shaded area would increase. Okay, and then in 5.3, they say use the collision theory to explain how a catalyst influences the rate of reaction. Okay, so what do we know? I'm going to write that in bullet point form. In fact, I'm even lazy to write. So the addition of a suitable catalyst, okay, I want you to keep that in mind. So the addition of a suitable catalyst, once I add a suitable catalyst, it lowers the activation energy, okay, of the compounds required, right? And so it means that more molecules now have sufficient kinetic energy, all right? So that would increase the number of effective collisions per second, and as a result, it would increase the rate of the reaction. Okay, I'm just lazy to write that down, so I hope that you understood it. Okay, remember we said we lower the activation energy, right? The addition of a suitable catalyst would lower that activation energy, right? So more molecules now have sufficient kinetic energy. It would increase the number of effective collisions per second, and thereby increase the rate of the reaction. This is me repeating so that you would understand. All right, now let's continue to the next question. Okay, it continues over to the next page. Now they say the reaction between powdered calcium carbonate, okay, and excess hydrochloric acid. Note that word excess there, because it simply means that the calcium carbonate would actually be the limiting reagent, right? They say to us, so they use it, okay, it's used to investigate the reaction rate at 25 degrees Celsius, okay? They say the balanced equation for the reaction is shown. Okay, there it is there. So they say several experiments are conducted, note that, using the same mass of impure calcium carbonate. So meaning that I wouldn't be able to use that mass that they've given me to calculate the number of moles. Why? Because there's some other hochakis in the calcium carbonate. For those of you international audience, when we say hochakis, it means other things that are not, calcium carbonate. Okay, right. So they say the graph below represents the results obtained. Assume that the impurities do not react. Of course, we'll assume that the only thing that causes that carbon dioxide would be the pure calcium carbonate. It only makes sense, right? Okay, so this is the average rate of production of carbon dioxide. They show us those points there. I'm sure we're going to use them later. Okay, now let's answer the questions. They say for this investigation, write down A, right? The controlled variable. Okay, now the first thing that you ought to note about a reaction is what exactly are we changing? So if you note in that reaction, what's our independent variable? Our independent variable is the initial concentration, in this case, of hydrochloric acid. So if what we are changing is the initial concentration of hydrochloric acid, all right, what do we need to make sure that remains constant? Okay, so what would remain constant would probably be temperature, right? The other factors that affect the rate of a reaction. You can even talk about, the state of division. Okay, we know they said we're using powdered calcium carbonate, so state of revision would remain the same. Okay, it would be a controlled variable. What else? It could be, so temperature. What are the other, factors that affect the rate of a reaction? Okay, yeah, you can just think about it. Surface area, you can think about, yeah, whatever it is that comes to your mind, what would need to keep the same, right? And then what would be the conclusion of this reaction? Remember, in your conclusion, you need to now tell us how would the independent variable affect the dependent variable. Okay? So in this case, I would simply say an increase in the initial concentration of hydrochloric acid would increase the average rate of production of carbon dioxide. Can you see? So all that you're doing is relating your independent variable, so your independent variable, right, as well as your dependent variable. So our conclusion would be an increase in the rate of in the initial concentration of hydrochloric acid would increase the average rate of reaction. Right. Let's go to the very last question, which I'm quite sure many of you would be looking forward to knowing how to answer that 6-mark question. So they say the calcium carbonate in 6 grams, okay, all right, is of the impure sample reacts completely, okay, with 0.3. Now, just a forewarning before I start there. So remember, this 6 grams is impure, so I cannot use that with number of moles to calculate the number of moles. Okay, so they say it reacts completely with 0.03 moles of moles per cubic decimeter of hydrochloric acid in 26 minutes. Okay, so I know that's the amount of hydrochloric acid, and I know the amount of time that it took, right? They say use the information in the graph to calculate the percentage purity. Now note, okay, the percentage purity, right, of the calcium carbonate. Assume that the molar gas volume at 25 degrees is 24,000 cubic centimeters. Now, let's start here. So remember, what are we looking for? Okay, we want to calculate the percentage purity. So it means that I must find out of this 6 grams, how much was actually the pure calcium carbonate. So you keep that in mind. So in a sense, what do we have here? We have information about calcium carbonate. So I'm going to use rate of reaction. I'm going to say, well, but I'm given the rate of reaction, isn't it? Okay. They told me when I use 0.03, so I'm going to go there and look for 0.03 and say, well, when I've got 0.03, they said, okay, let's look at that. I think that's going to be 50. So the rate is 50 cubic centimeters per minute. Can you see that? So the rate is made of volume. So it's going to be change in volume divided by change in time. I hope you can understand what I'm saying, right? So how I will calculate the rate of reaction here is that because it's given to me in cubic centimeters per minute, so I know it's going to be change in volume divided by change in time, and that time must be in minutes. Now, I know when I use 0.03 cubic centimeters, right, of moles per cubic centimeters, right, I will produce 50 cubic, so that's my rate. My rate will be 50 cubic centimeters per minute. But let's find out what is our volume, right? This is going to be the change in volume, right? So that is the amount of volume. Remember, you started with nothing. So it would be volume final minus volume initial. But how much volume did you start with of carbon dioxide? You would have started with nothing, isn't it? Divided by how long did it take for us to produce this much volume? It would have taken us 26 minutes. So I'm going to say 26 minutes. So let's find out what is our final volume. Remember that our initial volume would be 0. Okay, right. So I'm going to say, well, my volume that I will produce would be 50 times 26. Okay, so that's 26 times 50. and I get 1,300 cubic centimeters. This is the volume of what? Of carbon dioxide that I would have produced. Okay, now let's just go back a little bit. With this volume, I am now going to find out the number of moles. Remember, this volume of carbon dioxide would have been produced by the actual moles of calcium carbonate that reacted, right? So I'm going to use this volume to find out, I'm going to calculate the number of moles of carbon dioxide. And with that, the ratio is 1:1. And therefore, it means that I will now know the number of moles of calcium carbonate. So I'm going to say, well, the number of moles of carbon dioxide, okay, is going to be volume divided by the molar volume. Remember, they had given me the molar volume to be 24,000 cubic centimeters per mole, right? So in this case, I'm going to say this is 1,300 divided by 24,000, okay? Right, so what are the number of moles of carbon dioxide that were actually produced? This is divided by 24,000, okay, 24,000, and I get 0.054, okay. I'm going to just keep that answer there. It continues, these are moles, okay. But remember, the number of moles of carbon dioxide is, the ratio there is 1. But this tells me for every 1 mole of calcium carbonate, I produce 1 mole of carbon dioxide. So it means for any amount of calcium carbonate, you'll produce the same amount of carbon dioxide. So now what can I conclude? It means that the number of moles, okay, let me just get this guy away. So it means that the number of moles, okay, so therefore the number of moles of calcium carbonate should actually be also 0.054 ... moles. Okay, I just want you to get that. Why? Because the ratio is 1:1. As I said, ladies and gents, if you went and watched my video on stoichiometry, believe you me, these examples or these questions really become easier. This has got very little to do with rates of reactions, but it needs you to understand stoichiometry, right? So in this case, I just want you to notice something there. We now have the number of moles of calcium carbonate, but now we need to find out, okay, the mass, because we want to use that mass. So I'm going to use number of moles is mass divided by molar mass, right? But remember, molar mass for calcium carbonate, you can go and check in your periodic table. You'll find if you calculate the molar mass of calcium carbonate, okay, you will actually get 100, okay? So that's going to be 100 grams per mole. This is if obviously you use your periodic table. Okay, I'm just going to bring that closer here. Right, so I'm going to find out the number of moles calcium carbonate. So mass, okay, would be number of moles multiplied by molar mass. I hope I'm not going too fast, but as I said, we've covered this before. So this is going to be number of moles, that's that number, 0.054 ... Okay, multiplied by 100. I'm just going to take it as it is, just to avoid the rounding off. So multiplied by 100, and I get a mass of 5.4. I'm just going to say 5.42 grams. Okay, so it means of the 6 grams that was given, only 5.42 grams were actually pure calcium carbonate. Okay, so now we wanted the percentage purity. So we say, well, percentage purity is simply going to be the mass of calcium carbonate, of pure calcium carbonate, divided by the mass, the total mass, okay, that is inclusive of the impurities, and we multiply that by 100. Okay, so I'm going to take that number and divide 5.42 divided by, so that's 5.42 42, sorry, divided by the total mass was given as 6 grams, and you multiply that by 100. So divided by 6, okay, and I multiply that by 100 because I need to express it as a percentage, and I find that my percentage purity is 90 rather, 0.28%. Okay, right. That is the amount that I get in terms of percentage purity, right? And hopefully you do get this, ladies and gents. I didn't make it all that cumbersome for you to understand. All right, I hope that you understood that, and we'll see each other next time. Please don't forget to tell others about our channel. Tell them how much you are learning great things, and I'm sure this will help quite a lot, in preparation for your final exam. Please keep working hard, ladies and gents, and I will see you guys again next time. Sharp, sharp.